Recording is rolling. So, welcome to Wednesday. You guys are doing this friction lab. You guys have this page. Now, this friction lab is going to be in two halves. I'll tell you guys a bit about that. Hope you guys set that up. But I do want to remind you guys where we are in the context of the week. So, yesterday you guys did very non-frame. Today is going to be friction lab. Tomorrow I'll debrief the lab with you guys at the beginning of class. Then we'll solve some problems in the textbook. Tell you guys context of that tomorrow. And then we'll finish off the week, Thursday, Friday, with a centripetal force lab, which will lead into the next topic. You guys remember that there's an open notes take-home quiz that's been out for a few days, and that's due this coming Friday. It's on forces. And so I gave that to you a few days ago. And also through your fifth period class, the federal impact forms are going to be due by Friday. And so that's just some schedule reminders. But let's take a look at this friction lab. So question I might wonder is like, well, what's the coefficient of friction between two particular surfaces? You guys remember coefficient of friction is defined as the ratio of friction force to normal force for, say, like a free body diagram set up like this. And this is a material property. So once you know the two materials, it's determinable what that coefficient is. Thanks, buddy. So maybe I want to know like paper to paper, for example. Guess this lab weight that I've wrapped in paper? Why do you think I've wrapped it in paper? Because if I want to know a specific coefficient of friction, I have to control for the materials. And these lab weights that you guys have, well, some of them are just bare metal, whatever that metal is. And some of them are actually painted in that black paint, which is a different type of material. Right? So what is the coefficient of friction, say, between like aluminum and paper? Or say like wax paper and zinc or something, right? Once you know the materials, it's determinable what that is. And you guys can solve it today. But you're solving it from two different points of view, two different perspectives. Now, the first one, the one on the left, is actually very similar to something you guys have done here before. What I'm going to have you guys do is, do you guys remember the Sprigg Scales lab? It was like 10 mini labs. One of them was actually a shortened version of this. So, see, take different weights, say like at least 5 different weights for this table. Say, how much does this weigh? That is weight. Is that measured in kilograms or newtons? Weight. Hold on. Wait. Kilograms measures mass, right? And weight, isn't weight a kind of force, right? Which is measured in newtons, right? That's why it says newtons right here, right? So you guys gonna measure in newtons, and their newtons is well one side of the scale. Then next column over says the force to pull it, which is also going to be newtons because force is measured in newtons. Now I left off two critical details. There's a couple things that are implied here. One of the important details is that you're pulling horizontally, and the other important detail is that you're pulling at constant velocity. So when I say F pull, the implication is you're pulling horizontally at constant velocity, just like I'm showing right here. Now, why are those details important? Well, let's take a look at the free body diagram for what I just did. Okay? So there could be like some lab weight, maybe it's covered in paper to control for the material surfaces. So it's paper against paper. There's a weight, mg, straight down. There's a normal force acting up. And as long as you pull horizontally, remember that's one of those conditions I just told you, then there are no other vertical forces. Therefore, you can say that this normal force is exactly equal to the weight. And that'll be important later on. The other detail I told you is that you want to pull at constant velocity. Now, why is that important? Why is it important to pull at constant velocity? Because then the block would be in a state of equilibrium, all the forces would balance, right? Equilibrium might mean at rest or it might be constant velocity, but all the forces would balance either one. And because that would be true, I can say that this pulling force exactly balances with the friction force. Therefore, the force reading on the scale, that's what F pull is, the exact direct reading, represents the friction force. And going back to the idea of pulling it horizontally, that means that the only two vertical forces also balance out, which means that the normal force could be represented by the weight. Therefore, when you go to solve for a coefficient of friction, which is defined as the ratio of friction force to normal force, isn't that also the ratio of pulling force to weight? You could just sub those in there and be the equivalent. So that's what this is about. Then I want you to make a graph. And the title gives away what the axes are. So remember, the title is always y versus x. In this case, it says pulling force versus weight. So pulling force goes on the vertical, weight goes on the horizontal. Scale is start at 0, 0. And you guys also know the units for each of those. Remember, it's newtons and newtons. So I mentioned that earlier. So And I got a couple of questions out here. I want to see if you guys can figure out where I'm going with these or what to do with them. But the first one is the equation of the line on this graph. So once you plot a bunch of points, figure out what's that relationship. It's nothing too fancy, but if you know your algebra equations and the graphs that we've done so far in this class, then I think you should be able to get this. What was the equation of this graph? That's the first box. Okay, you guys good so far? Okay, so that's the first half of this lab. Then you guys are going to switch perspectives and also solve for coefficient of friction, but from a completely different point of view, using completely different measuring tools. Actually, this side, the only tool you really need is this right here, this protractor. I'll show you how you measure that. So you're going to start with a level surface, maybe a textbook or something that you can tilt up when we get. Throw a lab weight there, and then tilt it up. And hey, look, for the first few degrees, it just sticks to the paper, doesn't it? Just sticks there. But at some point, at some angle, it's going to break that initial friction. Oh, it's going to slide down. Right? And you want to record what angle that is with the protractor. Now, okay, so this column says weight. You'll pick several different weights. Try different ones. See, maybe it could be like independent variables or something. And see what angle does it break that friction. Now, I did leave off an important detail here too. I didn't specify angle relative to what. So while you guys are doing the lab, I will leave this slide, this free body diagram up on the projection so you can refer to it. This is really the second half of the lab here. And I'm talking about the angle relative to the horizontal, exactly as it shows right here. You see that? So you're going to measure how many degrees would that be. So using this protractor. I can walk around and help you guys for that too. But as a rule of thumb, it'll probably be in the ballpark of about 20 degrees, plus or minus, so somewhere there. Right? So look for a number that's about that number. Right. Then this last column says take the tangent of that angle. So for example, if your angle was like 14 degrees, you'd say what's tangent of 14 degrees? It'd be this decimal, and you just write that right there. Now, why do I want you to take tangent of the angle? Well, I don't want to give that away right now. I want you guys to think about that. So all day students have been stewing over, why is it tangent at the angle? And some students in some groups have gotten it. So some figured it out. So I want to see if you guys can. Right. Then make a graph, tangent theta versus weight. So tan theta, that's that mystery column. I wonder what that's about. As a function of the different lab weights that you use. So like this could be one lab weight. I wonder what this graph is going to look like. And then similar idea, I got a couple of questions at the bottom. One of them is going to be ultimately the equation of this line. See, if this axis is tan theta, they say tan theta equals, isn't that like y equals something? I wonder what that graph is going to look like. Right? And then there is a relationship between the two parts of the graph. I mean, there are different perspectives on coefficient of friction. Maybe there's one last detail I want to throw at you guys before I send you back there, which is actually on the second half of the lab, there's actually two different angles that you could be measuring depending on your perspective. So, and I'll let that a bit ambiguous. So as I was going over the directions, I said to be the angle that it initially breaks and then starts sliding down. Okay. But the other perspective you could do, which would actually result in a different angle, would be what angle do you need to keep it at so that it slides at constant velocity all the way down, which is actually a different angle. So I'll let you guys figure out which one you want to shot for. So just a little two different things you could be measuring. So figure out which one to do with that. Okay. Anybody got any questions so far? All right. So like I said, I'm going to leave this up here. That free body diagram, that might help you out quite a bit on the second part, and everything you do back there, and I'll walk around and help you guys out.